we're going to have a lecture on the hydrosphere. And I've got 4 topics that I want to talk about in regards to surface water flows and groundwater storage. Before I get into that, well, the first topic is where water is stored on Earth. And it really shouldn't be too surprising that by far the majority of water on Earth is stored in the oceans, 97.2%. But that's salty water, saline water, so that's not really quite readily available for human use. Then the remaining, really small amount, 2.8%, represents the world's fresh water. Right? And what we're going to do now is take a look at that little bit, 2.8%, and see where the fresh water is stored on Earth. So of that 2.8%, kind of surprisingly, 2.15 of that 2.8% is locked up as ice sheets and glaciers, and again, not readily available, for human use. And then groundwater storage, kind of small. I mean, just over 0.5%. That's pretty amazing. And then what you would think would probably be the largest amount of fresh water is actually minute, right? 0.02%, stored in lakes, the soil, atmosphere, and streams. And so that's kind of surprising. And so that's kind of where we've got this little sliver of 0.02%. Well, we're going to move on to a second topic, and it's an important concept in hydrology, geography, and geology. It is kind of a conceptual model stating that water is in constant movement between the ocean, the atmosphere, and the land. And you can just kind of imagine a water droplet and what can happen to it over various time spans. It can be evaporated from the ocean and then eventually condense and precipitate right back to the ocean within an hour. Or, it can form a humid air mass, a moist air mass, condense into clouds and then eventually precipitate. And it can take various pathways. And, it could be stored in a lake for a year or whatever and then eventually run off through a river back to the ocean. Or, it could infiltrate into the groundwater and be stored for like 100,000 years or 1,000,000 years. So there are various pathways and various time scales in which water is in constant movement. Now, as a matter of fact, we've actually been studying the hydrologic cycle. We've been studying the atmospheric portion of the hydrologic cycle, humidity, condensation, precipitation process. Now, in this lecture, what I want to do is talk about what happens to that precipitation once it strikes the Earth's surface, and it could take various pathways. So that's the third topic. I want to talk about 2 surface water flows. Now, I'm not going to talk about river flow. That's going to be a major topic at the end of the class. I want to talk about number 1, infiltration, the rate at which rain seeps into the soil. And it's really, really important. That's what you want. You want rain to seep into the soil so you don't wind up with surface flooding. Now, I'm going to talk a little bit more about infiltration because it does depend on several things. And one thing is the grain size of the soil and the dominant grain size. And so let's just imagine you've got a really sandy soil. Now, in terms of grain sizes, sand is relatively large. Meaning if let's say you go to the beach, you can actually pick up, a handful of sand and you can actually see an individual sand grain. It's a couple millimeters in diameter. And so this top diagram is kind of representing sand. Right? There's a joint there you don't really need to worry about. But so they've enlarged sand grains like 1,000,000 times, right? So the point is that if you've got large individual grains, that means the way they fit together, the pore spaces are going to be large too. And so that's what you need is large pore spaces so the rain can seep on through. And so you're going to have high infiltration. And In Florida, for example, I mean, they have very, very sandy soils. And in a way, they've got too much infiltration. They get a lot of rainfall, but what winds up happening is the infiltration is so great. I mean, the water immediately seeps to the water table and is not available to the roots of the trees. And so they actually have even though they get a lot of rain there, they really have a lot of drought conditions too, because they've got too much infiltration. Let's do the opposite. Let's talk about individual clay grains. Now, down here we're kind of illustrating clay grains. Now, clay, all right, an individual clay grain, you can't see it. You need a scanning electron microscope to actually see an individual clay grain. All right, so here on the bottom, we've multiplied the size of the clay grains again by about 1,000,000 times. But the point is, if you've got tiny individual mineral grains, the way the pore spaces are going to be, they're going to be tiny too. So you try to imagine a raindrop or a rain trying to seep into a soil with little or tiny pore spaces. It really can't do that. And so you're going to wind up with low infiltration. Now, in Louisiana, we do have a lot of clay soils. And so that is certainly, one of the factors that, causes us to have flash flooding and surface flooding. We're flat too, and we do tend to have really intense precipitation events. And then on top of that, we tend to have clay soils. So we do have a lot of flash flooding here. All right. Yeah, another factor that determines the infiltration rate, which you want, is previous moisture. If it's been dry for a long time, I mean, the pore spaces of whatever soil you have, the infiltration is going to be pretty high, as best as it can be, depending on the soil that you have, because the pore spaces are empty, and so you've got plenty of availability, right, to fill in those pore spaces. Now, if it's been raining, we certainly have periods of heavy rain for weeks on end, and over that time, I mean, the pore spaces are filling up and filling up and filling up, and then you're finally at capacity, and you're getting more rain. And so what you're going to wind up with is, low infiltration and surface flooding, because the pore spaces are already filled. And I know you've seen that before when we have really wet conditions. And a third and final factor that determines infiltration is the condition of the soil surface. All right. And I mean, if you've got a hard, compacted surface, like is illustrated here, that's pretty bad. I mean, it's really going to be hard for the rain to infiltrate in. And what you're going to wind up with, again, is, it's not going to infiltrate. Where is it going to go? It's going to wind up, creating a flash flood. This is really common in desert environments. Now, we get flash flooding for the reasons that I had just mentioned, but it's kind of really common in the desert. It's kind of famous because there is little vegetation to protect the surface, and the surface is baked, throughout the year with the clear skies and low precipitation. When you finally do get a rainfall event, none of that rain can actually infiltrate on down, and it just flows over the land into a low spot, and within literally minutes, the dry stream channels in desert environments turn into raging torrents, flash floods. And so indeed you have, when you have hard compacted surfaces, you have low infiltration, and flash flooding is certainly common, very common in desert environments. I don't have a picture here, but just kind of imagine, a wet environment like here, kind of the eastern United States, where you've got, well-vegetated surface, with grass or even weeds, but trees and bushes and shrubs and things like that. And so, if you've got some sort of vegetation cover, that's going to keep the surface shaded, right? And, and also, all of the vegetation's got roots. And so that's going to help to keep the soil surface open, right? The pathways open. So in general, you're going to have, much better conditions to have the rainwater seep in. And so you'll have, better infiltration when you have a vegetated, protected surface. All right. This is the second, right, surface water flow. So we've just talked about infiltration, and that's kind of what you want, right? You want the rain to be able to seep into the soil. Now, I've been talking about, flash flooding, if you don't have infiltration. And really, this is that, okay? We've got two terms for, flooding or flash flooding. It's called overland flow, right, if you don't get infiltration. And another term that's really commonly used, runoff. So these two terms are used interchangeably. And obviously, you get overland flow or runoff, and it's going to occur when rainfall, is greater than the infiltration rate. And what's going to wind up happening is the rain is going to wind up flowing in broad sheets over the surface, and then it's going to start to accumulate in low spots. And so here's kind of a winter scene around here, and so you wind up with erosion. That's kind of the bad thing about overland flow, particularly in the dormant season when you've got the bare soil. You wind up, with the capability of flooding and eroding the topsoil, which is the most fertile. And so you wind up starting to create rills and gullies. And in really fragile environments, this was taken near Austin, Texas, you wind up starting to create rills and gullies, and then eventually, they get deeper and deeper and deeper, and you wind up with land that's virtually unusable. If this picture is taken in Texas, it's cattle country, it's ranching country, and literally, the land becomes unusable because, you can't put cattle here. You cannot do that. And so here's the figure from the book. There's infiltration that we were talking about, and if you don't get infiltration, you wind up with overland flow. And so overland flow is bad, right? It winds up eroding the surface. All right, the fourth and final topic is water stored in the subsurface. And what I'm going to do here is introduce, various terms. Groundwater. Right. What is the groundwater? It is the saturated zone in the subsurface, meaning that it is the zone where all the pore spaces are fully saturated with water. And so what we have is, long periods of infiltrating water, over thousands or hundreds of thousands of years, millions of years. And eventually this infiltrating water will start to accumulate and start to fill up the pore spaces and some deep underground surface. And eventually, you're going to, start filling up the pore spaces and filling up the pore spaces. And so the groundwater is where all the pore spaces of the rock or sediment, whatever it is, are fully filled with water. It's called the saturated zone. All right, now there's a term that you've heard before, is the water table. And the water table is nothing more than the top of the groundwater zone. All right, now you can actually see the water table if you dig a natural well, because what's going to wind up happening is because you've got all the pore spaces are filled. You've got water pressure, and so you've got an empty area here, and so the water is just going to wind up through water pressure. It's going to fill in that gap. And so if you look at a natural well and you see the level of standing water, well, that's going to represent the water table. Or if you've got a depression, again, you've got all that, what's called positive pore pressure, when all the pore spaces are full, and it's going to build up pressure. So you've got a depression, right? And any area below the water table where the pores are saturated, it's going to fill in that depression. So you can see the level of the water table just by looking at the level of a lake or a pond or a marsh. Now, the water table fluctuates. During, very, very rainy periods, the water table will rise, and the level of water in the well will rise, and level in the lake will rise. Or during very, very, very dry periods, your well, might dry out, and the lake will get lower, and the marsh will get lower. Yeah, so you could dig a hole in your yard. Of course, here in South Louisiana, the water table is quite high, and within a foot. You just dig a hole in your yard, and the base of that hole will fill on in. But there are areas in the United States where you have to go on down hundreds of feet, all right, or thousands of feet to actually, reach the water table. So, but here, when I was a graduate student at LSU, we were doing soils and we were digging holes and, kind of shaving it out often, and we're taking soil samples. But in this one hole that we dug, I mean, it didn't take very long for the bottom of the hole to fill in, and it stopped filling in at this point, and so there's the water table, and this was kind of in the Feliciana area, northeast Louisiana, and so you can actually see the water table if you dig a hole around here for sure. All right, another term, we don't use this so much, but it's called the unsaturated zone. And it's the zone of infiltrating water. So you've got the soil, all right, and the rain is seeping through the soil, and then it kind of continues on down until you reach, the saturated zone. And so the unsaturated zone is just partially, the pore spaces are just partially filled with water. So, after a rain, the pore spaces will be more filled, and if it's been dry, you'll be less filled. All right, another term, aquifer. Now, this is a term actually in geology. An aquifer is actually the geologic deposit that stores the groundwater. Now, there are good aquifers and there are bad aquifers. Now, a good aquifer would be some sort of geologic deposit that has large and interconnected pore spaces to store the groundwater, and that's what you need. Right. Now, we haven't done our geology section yet, but I think you might understand this. So, in the subsurface, we've got, different geology, and particularly here in Louisiana, I mean, we've got a lot of clay layers, but also underneath those clay layers, we've got sand and gravel layers, deposited by the Mississippi River during the Ice Age. And so we've got really deep, thick deposits of sand and gravel, or sandstone. If you remember, I gave you the example of sand, that has large pore spaces. Well, even the rock form of sand, has good pore spaces. Limestone is almost like a sponge, all right? And so that's also, if you've got limestone rock in an area, that's going to form a really good aquifer. And let me just kind of go back to sand. I mean, if sand grains are large, gravel is even larger. So the way gravel grains are going to fit together, you'll have nice big pore spaces. So that's what you want. I want to talk to you about a really good aquifer that we have in Louisiana, and it creates really delicious water. It's called the Southeast Louisiana Aquifer System, and I've just kind of got it highlighted here in Louisiana. It's basically north of the lakes, and it does extend into southwest Mississippi. And about 1,000 or 2,000 feet below the surface is a really thick sand and gravel layer deposited during the Ice Age. And this is a beautiful aquifer that's storing the groundwater because this one aquifer lacks a lot of mineral impurities, and we call that kind of water soft water. And so it's not hard water. Hard water would have like iron in it that stains your porcelain in your bathrooms. Sulfur is a mineral impurity that makes the water stink like eggs. Salts, calcium carbonate is common in the desert that kind of gives a chalky taste to the water. And so that would be hard water, but this is nice soft water. And as a matter of fact, I mean, the towns and cities in this area in Louisiana, as the so-called Florida parishes, they actually dig their municipal wells, and that's why I live in Baton Rouge. The water is pumped up from this aquifer, and it really is delicious soft water, but even Hammond and other areas too. And then entrepreneurs, several decades ago decided, to pump this water on up and and sell it. And so, of course, Kentwood, Louisiana is located here, and they pump up this groundwater and from the sand and gravel aquifer and they sell it. And the same thing with the Beata Springs, right? So you might have one of these companies deliver water to your home. Now, I don't need that in Baton Rouge because my tap water is this water, and so that's one of the reasons why I've been commuting to Thibodaux for the last 31 years. Of course, Thibodaux is Mississippi River water, all right, and we're at the end of the line, all right, and so it's a lot of polluted water, unfortunately, and they put it's heavily chlorinated and what have you, and so it's not really quite as good as the Southeast Aquifer system. All right. All right, as I had mentioned, there are good aquifers, like I had just talked to you, with big pore spaces to store the water. And it's, again, geology. All right, so a bad aquifer in geology is called an aquiclude. And this is some sort of geologic deposit, rock or sediment, that literally stops the flow of water in the subsurface. So it has, this geology has tiny pore spaces, or even no pore spaces to actually stop the flow of water. So I gave you the example of clay grains, a clay soil, and so if you've got a clay layer, a thick clay layer like we have in Louisiana, that'll be an aquiclude. Now, the rock form of clay is called shale. And so if clay is bad, well, the rock form is bad too. So that's also an aquiclude. And any igneous or metamorphic rock that has crystals in it, no pore spaces, definitely is an aquiclude. And I just put granite down here because you're kind of familiar with granite, granite countertops and things like that. And so there's no pore spaces in this, it's just crystals. And so that's a good example of an aquiclude. All right, another term is artesian water, artesian flow. And I've got some examples here of, here's an artesian spring coming out of a river. And here's an artesian spring in Colorado, and they've actually made it into a well. All right. Now, a lot of people are kind of surprised by the actual definition of artesian. All right. This is it. This is the definition. Groundwater in the subsurface is able to flow to the surface spontaneously without pumping it on up. All right. And so here we go. So can you imagine? Canoeing in a river and you see this, right? That's artesian water. That's artesian water flowing. It's an artesian spring. Now, a lot of people are kind of surprised by the definition, can flow to the surface without pumping. That word artesian is kind of one of those, I don't know, there are certain words that are kind of nice words that people, it's almost like French words. They sound so lovely, not Cajun though, I don't know. But it sounds as nice as the true French dialect. But anyways, artesian, a lot of pumping companies, water bottling companies, like to use the word artesian because it just sounds nice. And back when bottled water started to become popular in the 1990s, bottling companies would always put on their, on the bottle, from our fresh artesian springs. But in reality, it's not artesian. They'd pump it on up. And actually, the federal government cracked down eventually. If the water is not artesian, you cannot use the word artesian because it just kind of brings to mind, fresh, natural, spring water or something like that. But this is the actual definition of it. Now, in order to get water to spontaneously flow to the surface without pumping, it takes a special set of geologic conditions, to build up enough pressure to get water to flow to the surface without pumping it. And what you need three things. You need what is called a recharge area. And so you need rain, okay, to fall on an exposed aquifer. So right here, we've got an aquifer, sandstone layer here, and it's exposed at the Earth's surface. And so what you need is rain, all right, to fall on that exposed aquifer and fill in the pore spaces. And then, of course, the water will, will move through the interconnected pore spaces. Now the problem, recharge areas are becoming paved, through the expansion of suburbia. And it's and so what's winding up happening is recharge areas are becoming few and far between, and municipal areas are starting to zone off a recharge area so they can actually protect the water supply for the city. And again, this is in Texas. This is in Austin, Texas, actually way out in the suburbs. And and that's a big city. And so they've got to supply water, through this limestone aquifer. But they're building suburbia outward and outward and outward. And there's just a certain point where you got to stop paving to protect the recharge area. And so they've cordoned off, hundreds of acres to protect the Edwards, as it's called, the Edwards Aquifer Recharge Zone, to protect the water supply. All right, so you've got the recharge area, and then obviously also that is shown you need sloping rock layers, to get the water flowing, through the pore spaces. Plus, you need sloping rock layers too to have your aquifer, exposed at the Earth's surface. And then the third thing that you need is something called a confined aquifer. All right, that means you've got an aquiclude above, all right, and below the aquifer. So here we've got some impervious rock. That means, like shale or clay with, no pore spaces. And then this is the symbol for granite, some sort of igneous rock without pore spaces. And so that would be an aquiclude. And so what you wind up with is, a confined aquifer, and that really helps to build up pressure. And so all you need is maybe fractures in the rock, or you dig a well, and the water, right, can actually, now you've built up enough pressure, you've got enough water flow, and you actually create an artesian spring, or you dig a well and create an artesian well. Now, sometimes the artesian water will just be a little trickle if it's been, been dry, or it can gush forth, tremendously if it's been, really rainy. I do want to finish up by just making sure you understand the difference between an artesian spring and a geyser. Now, a geyser, like Old Faithful, that's water flowing forth without pumping, but it's it's hot water and steam. And so the mechanism of getting the water to flow spontaneously to the surface is totally different. And so a geyser has a volcanic heat source. Actually, Yellowstone National Park is basically a volcano that hasn't made itself yet. It's got hot lava very close to the Earth's surface, and the groundwater is constantly moving over that that hot lava, becomes heated, expands, creates pressure, and then rises to the surface through fractures. And so whatever, it takes about an hour and 20 minutes or so for the groundwater to get heated, expand, and then flow. And then do it all over again. So it is pretty much timed based on the rate of groundwater movement and the temperature of the magma. That ends lecture number 8.